Hi, today we're going to start off Chapter 10. We're going to move right on into some new topics. So we're going to get started with a quick reminder of some prior content that might be of use later. So in determining the ionic strength of a 0.02 molar calcium chloride solution, first we need a chemical formula. So that should be pretty easy to get, CaCl2. We're going to change our color really quick because I forgot. And then don't forget that the ionic strength equation is 1/2 times the sum of the charges times the concentrations for each ion present. So that would be 1/2 times the concentration of calcium, which is 0.020 molar, times a plus 2 squared plus 0.040 molar, because remember, with the two chlorides, you get two chlorides for every mole of compound, times -1 squared, which should give you, I wrote this down so I wouldn't have to do the math, 0.060 molar. So just a quick reminder of how that works way back from Chapter 7. So getting started, this is probably what you've seen before when you've looked at a titration curve. And I think in the past we've mostly been worried about calculating the concentration of base added at the equivalence point, and you may have actually seen the formula before, MAVA equals MB VB, where we call the volume at the equivalence point. For this course, we're going to add a couple layers. We're going to call that V sub E, as in equivalence volume. And this is all this should be something you're very used to. What we haven't necessarily done before is we're now going to say, okay, what's the pH at 20 milliliters of base added? What's the pH at 22.6 milliliters of base added? And hypothetically, we want to come up with a series of equations that would allow us to construct a pH curve from at any point, at any amount of titrant added. So in order to do this, I'd like to kind of step into one example problem and work our way through it. I'm going to take the chance to show you how you may have seen it in an earlier course, like AP Chemistry, and then show you another way of looking at the problem that might give you an easier set of calculations. But regardless of the situation, the first two steps are always going to be the same. We need to write out a balanced chemical equation, and we need to calculate our equivalence volume. So potassium hydroxide plus hydrobromic acid, simple double replacement reaction should make water and potassium bromide. If you can't remember the process for net ionic equations, split everything that can ionize into what it ionizes into. Cancel out anything that is a spectator unchanged to the reaction, and our net ionic reaction, which should be the net ionic reaction for any strong acid, strong base titration, would be hydroxide plus hydronium yields water. Of course, the phases need to be in there as well. And then we should also calculate our equivalence volume. Since we are titrating a base with an acid, we're actually trying to calculate VA. So a rearrangement, our VE, which is equal to VA, is going to be equal to 0.0200 molar times 50 milliliters. And we can leave this in milliliters because we're going to use our answer coming out in milliliters, divided by 0.100 molar, and we should get 10.0 milliliters of acid to complete this titration. In terms of how we're going to look at this titration, the way I see it, there are 3 different regions we're going to worry about. I'm worried about that region, which is the exact equivalence point. I'm worried about all the area of space where you're not at the equivalence point, and then all of the area of space where we're past the equivalence point. Basically, we're going to treat each region with a different set of math, and so we need to delineate what volume regions, x-axis spaces, are different in terms of the chemistry and the math that we're going to carry out. So the first one is going to be our current volume is less than the equivalence volume. Our second region will be where the current volume is equal to the equivalence volume. And our third region is going to be where the volume is delivered is greater than the equivalence volume. So 3 sets of calculations shouldn't be terrible. Let's dive into it. But first, a little bit of vocabulary. Yes, I know I spelled it wrong. I'll fix it for next year. There is a slight difference between the equivalence point and the end point, and it's worth talking about in this course, just for a little bit. We should probably, do I need more colors? Do I have the right color? This is a good question. Is my marker even working? There it is. Is that purple? It's dark blue. That's purple. That'll work. The equivalence point is the point that you're seeing on the graph where the pH is 7. For a strong acid, strong base titration, that is true, but it's really the point where the amount of analyte is equal to the amount of titrant. Usually we're going to measure amount in moles. So moles of acid, H+, equals moles of hydroxide. The moles of acid you have equals the moles of hydroxide added, or the other way around. The endpoint, which is not always the same thing, is the what you observe. Sometimes it's called colorimetric, where the indicator present, instead of a pH probe, is actually indicating, changing color. Depending on the source you're looking at, the pH range for phenolphthalein to change color is between 7 and 9 or so, usually between 8 and 9, depending on, again, the source you're looking at. So that would be any region in the y-axis above this line that is not really being drawn as a line. In pH ranges above here, the solution will be this pinkish purple color. In pH ranges below that, it will be colorless. So the question becomes, how different is it between the equivalence point and the end point? And hopefully you can see, I mean, we could probably do the calculations at the end of this if you're curious. Maybe I'll record that as like a second video, something worth looking at. But the x-axis space, the volume of base added needed to get between a pH of 7 and a pH of 8 is nothing, is negligible. It's going to be at the limit of detection for any method you have. So that's why usually, at least in a strong acid, strong base case, we say that the equivalence and the end point are negligibly different, and it's okay if it doesn't quite line up, because you're not going to be able to measure it with most tools. So, but before we dive, I keep saying before we dive into this, I do want to talk about what we're going to call region, and we can put air quotes if we want. I'll call it region 0. And that's where the volume added equals 0 milliliters. So I'm not really calling it a region, and we can still use the same math once we get to the end, and I'll try and remember to go back to that. But you can use that, because it's good to establish, well, where we're starting. And here they told you it's 50 milliliters of a 0.1 molar HCl solution, so the pH there is 1 because you haven't added anything. And so all we really have to do is look at the thing that's actually present, and we have this. That's going to be our potassium hydroxide concentration. That's going to be our hydroxide concentration. So pH should be equal to 14 plus log of hydroxide, which in this case is going to be equal to 0.02 molar, and the pH that we get out is 12.301. We're good? We're good. So, like I said, Region 1, we're going to dive into our AP answer. Hopefully this is a bit of a review. If it's not a review, well, you're probably going to want to write this down. We're going to calculate the pH of solution when we've added 3 milliliters. So we still know we're in Region 1, because volume is less than the equivalence volume, which in this case was 10 milliliters. So obviously 3 is less than 10. And the way we would address this is we know from our balanced equation, our net ionic equation, H plus OH minus yields water. And we're going to set up, we're not an ice table, we're going to do our initial, change, and final, because this is not an equilibrium. We're actually finishing the chemical reaction. We need to figure out what's left after they've done their reacting, and that's going to be the important part for figuring out the pH. Now, water being a liquid, we're not going to worry about concentrations, we're not going to worry about moles, because, well, it's a liquid. We're worried about the aqueous components, the things that are present in measurable quantities of analyte and titration. So we should enter into this moles, not molarity, because there's something to worry about with this, that we're adding liquid to liquid, and volumes are additive, so that's going to change things. But in both cases, we should calculate moles, and the moles of acid added initially are going to be equal to 0.00300 liters. Oh, sorry, one too many zeros. Times 0.100 molar, or 0.00030 moles. And that'll be our initial amount of H+. And for the amount of base, we're going to do the same exact thing. We have 50 milliliters. Zero two zero zero molar, and that will give us 0.0010, I guess 0. Yeah, moles. And that's our moles of hydroxide. Keep in mind we're starting with hydroxide. 0.00100. So if we do our subtraction here, we're going to subtract the number that we actually, like the smaller of the two, obviously limiting reactant, 0.00030, 0.00030. Yes, we make 0.0003 moles of water. Great. We had plenty of other moles of water there too. And we're left with no acid and 0.00070 moles of hydroxide. But you don't use that number because that's moles and not molarity, and we added 3 milliliters to 50 milliliters. So to figure out the actual concentration of hydroxide, we need to use that number, but divide by the volume, the new volume, the summed volume, which would be 0.0530 liters. And that should give you a concentration. I wrote this down so I wouldn't have to remember it. 0.0132 molar, which would then give you a pH value of 12.12. Cool. So that's a nice review of how everything worked. Something I want to point out now that we're actually here. This is a strong acid, strong base titration where we start low and end high. This is a strong acid, strong base titration where we started pretty high and ended, well, not ended, but we've progressed down. So I think what we should not forget here, since this is a strong base, strong acid titration, that we're going to start at a higher pH and then a lower pH. So the pH, the curve should actually look the same, just, a little reflected. Something like that. And so it makes sense that our initial answer was 12.3, and now we're at 12.1. So as we continue on, the pH should steadily go down until we get, well, not steadily, but it's going to go down until we get to the equivalence volume. But we can probably speed up this process considering two factors: the fraction of analyte remaining and the dilution due to the added volume. So looking at these numbers, we might be able to reason out something simpler. If you notice, we've got a 3 here, and there's a 3 here in our acid. And there's a 1 here, and I don't see any 1s in the base data, but I do remember if we go back to our equivalence volume, that was 10 milliliters. It turns out that the mole ratio will actually follow a volume ratio as long as you're only talking about the volume of titrant added. So as long as we're only talking about the acid that we've added, you can kind of consider the amount of base that's left remaining almost a percentage of the equivalence volume. That is to say, let me write out the equation, that the at 3 milliliters, and I'm going to get to the 5 and the 9 in a second. I just want to make sure we can get the same answer. At 3 milliliters, oops, that should be that's not millivolts, that should be milliliters. And if the equivalence volume is 10, this represents 30% done, or 70% left. So you can almost say that the amount of hydroxide that's remaining in the solution is 70% of what you started with. But then also you have to consider the fact that adding the 3 milliliters diluted down your total volume, so you diluted your total concentration down. So what we're going to say is that the amount of hydroxide at any given time should be equal to, the concentration, should be equal to the original concentration times the percent left times some dilution factor. And we know, remember from dilution, that dilution is M1V1 equals M2V2. And so really what we can say is that M2 is equal to M1 times V1 over V2. And so since we've already gotten M1 right here with our initial hydroxide, this V1, V2 should show up over here in our dilution factor. So that means that for the OH minus at a volume of 3, it's going to be equal to 0.020 molar times, and so what I would say over here is 70%, but I'm going to write it I'm going to write it down here, as 0.7. And then for our dilution factor, we started with 50 milliliters, and then our total new volume is 50 plus 3, or 53. I'm actually going to write 53, because I'm going to write this all out in ways that make sense, and I'm going to turn it into algebra that hopefully still makes sense. And then if you do all that math, did you pause the video to do the math? I hope you did. You still get 0.0132. Within reason. I mean, I'm not sure if rounding errors are going to pop in. When we're writing the percent left, the way I want to write the percent left is kind of like this. Or not kind of like this. It's exactly like this. I want to say that the percent left is equal to the equivalence volume minus the volume added over the equivalence volume. So in this case, that would be 10 minus 3 over 10, or in other words, 7/10 or 70%. This works well when your equivalence volume isn't like 10, and so your percentage left might be a little bit more obnoxious of a calculation than you want to make. And then for the dilution factor, I want to say that the dilution factor is going to be your, how do I want to write this? In this case, I'm going to call it VB. Because we're starting with base. So our initial volume of base, because this is relative back to the hydroxide solution, over VB plus V. And this would give you that 50 over 53 that we saw before. So what's kind of nice about this formula is we can kind of do this over and over again. And then if I say we want to do this at 5 and 9 milliliters, all you have to do is substitute in 5 and 9 for those two V values. So what you should be able to do is to say that the hydroxide ion concentration at, say, 5 milliliters is equal to 0.020 molar times 10 minus 5 over 10, which again would be 50% or halfway done, which is true when you're at 5 milliliters out of 10, times 50 over 50 plus 5. And going through that, you should get a hydroxide value, if you do the calculation, of 0.00909 molar, which is a pH of 11.95, which, again, pH went down slightly, which is good, from the to the 12.12 before. And then if you're going to do the same thing for the hydroxide at 9 milliliters, the same thing except there'd be a 9 here and a 9 here, you should get that the concentration comes out to be 0.00169 molar, which would then yield a pH value of 11.229. And what's really nice about this equation is you can really push this. You could say 9.9 and 9.99, And you don't have to get into these mole calculations that give you like 10 to the minus 6th and 10 to the minus 7th or some ridiculously low number. And so you can keep pushing this until you get to 7. And then when you're at 7, we can do all the same math again. But what you end up finding out is that this is 0.0010 moles. So initially, this is 0.010 moles and 0.0010 moles. Because we did that before, it's the same hydroxide. And so the final is 0? Oh, right, but it's water, right? So even if you have no OH minus and no H plus left, there's always water, and so water always reestablishes equilibrium, so you can figure out the H plus very easily because Kw equals H plus times OH minus, and since you killed all your chemicals, not killed, but if you removed and reacted out all of your chemicals, the H plus concentration is equal to 1 times 10 to the negative 7th molar, and the pH equals 7. Yay! Strong acid, strong base titration, always 7 at the equivalence volume. But we know more than that at this point, because this isn't just H plus plus OH minus yields H2O. This is two ionic compounds reacting. So really what's taking place is when you get to that full equivalence, yeah, all the H pluses and OH minuses have reacted, but you still got some Br minuses and some K pluses floating around, and we know that ions affect equilibria. That ionic strength is still a thing. So what we need to do is we need to figure out what the ionic strength of this solution is at the equivalence point. Now at the equivalence point, that kind of means that all of your salts have diluted each other. This isn't 10 milliliters of stuff, and it isn't 50 milliliters of stuff, it's 60 milliliters of stuff, where this 0.1 molar is the initial concentration of the 10. So your bromide concentration has actually been diluted. And it went from 10 milliliters to 60. So that'll be 0.01667 molar. And the potassium concentration is 0.020 times 50 over 60. Oh, it's the same thing. And since these are both +1 -1 salts, then we know that the ionic strength is equal to 0.01667 molar. You guys see why I brought back up that ionic strength calculation? I also think it's getting darker in here. That's fine. So using these two values, that's our ionic strength, we should be able to figure out the activity coefficients for H plus and OH minus. Oops. Now looking at this, looking at our ionic strengths that are over here, just a quick reminder of Chapter 7, I don't see 0.0166. It's somewhere between these two. So hopefully the numbers we get are somewhere in there. I'm not going to do the extrapolation method. I'm going to do the Debye-Huckel formula. I prefer it. So plugging into the Debye-Huckel formula for that will give us a gamma value for H plus of 0.896, which is definitely in between these two numbers, and an hydroxide concentration of 0.876. So then we know that Kw is equal to the activity of hydrogen times the activity of hydroxide. So if you go through all that math, I believe what you get is the H plus concentration. Feel free, you know what? No, I'm rushing. I'm going to save time in the video, but I do want you to pause and actually do this to make sure you remember how this all works. I'm trusting you here. Okay? So you went and you paused. And you got the answer? Yeah? Did you? Did I? 1.129 times 10 to the minus 7th molar. I think I'm getting close to my head again. Now don't forget for the pH that you're also going to be taking the negative log of the activity. So that's going to be 1.129 times 10 to the minus 7th times 0.896. And when you do that, you get 6.995. So it's not a big difference, but it is nice to know that we have at least added something to what you learned in AP Chemistry. I appreciate being able to do that. And then finally, we should take a look at what region 3 looks like. In region 3, you can see you've added V is greater than VE. So we've added our H plus moles. Our hydroxide moles is still 0.001. I don't care about the H2O. We're done with it. We're good. Cool. And the H plus added is going to be equal to 0.00105 moles. So in this case, we're going to again use the limiting reactant, 0.0010, 0.0010, and what we get is 0.00005 moles of H plus. Oh my God, that's so much. I mean, it is, because then you got to figure out what the pH is. So this is going to be our moles of H plus. So in this case, we're actually solving for the molarity of H plus and not of OH minus, because we've got excess acid. 0.00005 moles over, we had 50 and 10.5. Did I do my math right? I really hope I did my math right. Oh, I'm going to be kicking myself. Oh no, I did do my math right. Sweet. 0.0605 liters, and that gives you a concentration of 8.26 times 10 to the minus, wrote this down, 4 molar, and your pH here is going to be equal to 3.08. Said it, and then I wrote the other thing. I think it's been too long since I've been in the classroom. And 3. So again, our pH dropped dramatically, even half a milliliter after the equivalence point. So from the same number, where'd it go? Oh no. Oh, the words didn't cover over. Oh well. Damn, there's no copy and paste function, is there? Nope, it doesn't matter. We're going to do the same thing in a different way. Now, instead of setting the same thing up as last time, it's going to look a little different. So now we're going to say the H plus concentration at some time I or some volume I. It's still going to be a dilution of the original concentration of H plus, but the difference is we're going to really just do the dilution of what's in excess. Over the total volume. That's going to be equal to the original volume, the volume added minus the equivalence volume over the volume of base in this case plus the volume added, because we're doing the total volume of stuff we have. This is the fraction that goes in here. So what we're going to get here is we have 0.100 molar, and we're going to say that this difference is 0.5 milliliters divided by 60.5 milliliters. And what we get is the same 8.26 times 10 to the negative 4th molar, and the same pH of 3.08. So hypothetically in this case, you can use either. I'm not worried about which method you use. I support using the AP Chem method that you've learned before if you remember it. This just feels like more work to me than this does. But this involves a new formula that you're going to have to kind of reason out, and don't get me wrong, I make mistakes with this all the time too. So I support either method, which is why I showed both to you. Hope this helps. Thanks for watching.